Eutrophication begins with an excessive input of nutrients. Too much nutrients leads to increased growth of phytoplankton. The amount of organic matter is increasing, and this in turn triggers a series of physical, chemical, and biological changes in plant and animal communities, as well as changes in processes in and on sediment. When production of organic matter exceeds the normal consumption of the system, the oxygen in the bottom water consumed when increased amounts of organic material, algae, plants, and animals falls down on the floor and exploded. Surplus material to be broken down and large bottom areas will suffer from lack of oxygen and decreasing quantities of demersal species. If the level of oxygen is less than 2 milliliter per liter fleeing fish, when all the oxygen is used up to the formation of hydrogen sulfide during the decomposition of organic matter, hydrogen sulfide is toxic and kills all demersal animals can't escape. One of the eutrophication effects are that blooms of toxic cyanobacteria. These organisms are leguminous, which means they can be air content of nitrogen of their own growth. The leguminous cyanobacteria brings the Baltic Sea near 400,000 tons of nitrogen per year. It's as much nitrogen as people contribute by emissions. In order for cyanobacteria to be able to increase, they need large amounts of phosphorus. Therefore, it is believed that the solution to the problem of toxic algal blooms is to eliminate discharges of phosphorus. But it has been shown that the amount of phosphorus in the system linked to the amount of nitrogen in large quantities gives increased production of other algae, resulting in more oxygen-free beds. And the oxygen-free floor releases phosphorus. This can be used to cyanobacteria growth. The reduction of nitrogen and phosphorus pollution must go hand in hand, and the answer to whether nitrogen or phosphorus should be reduced is both. Agricultural use of fertilizers increased sharply after the Second World War. Therefore, the output of phosphorus and nitrogen into the lakes and coastal areas considerably larger today than the beginning of the 20th century. Farms use large amounts of chemical fertilizer. Arable land is also often manure. The risk of phosphorus and nitrogen escaping from the cultivated fields to adjacent watercourses, lakes, and coastal areas are affected, among other things, of which is the crop is grown, type of soil, rainfall, irrigation, and harvesting. On average, a third of the nitrogen in matter is arable land, but to be useful because it's not taken up by the crops. More than half of this surplus is leaking out into the surrounding water. From rivers and streams, naturally, a lot of nitrogen and phosphorus that ends up in the ocean. About a quarter of the total nitrogen and phosphorus application rates via the rivers around the Baltic Sea and Västerhavet are derived from natural sources, but the rest, i.e. 3/4 of the supply, are anthropogenic, that is caused by man. First and foremost, the emissions from sewage treatment plants and industries, as well as leakage from agricultural land and woodland, which are the main sources. Wetlands drained, lakes have been lowered, and rivers which been resolved out, contributing to today's major nutrient bleaching pressures from agricultural areas, because leakage ceased to be checked in the same way as before. Rainfall today contains significantly more nitrate and ammonium than it did before the Second World War. Car transport and shipping are the main sources of NOx emissions, and while the deposition of ammonium due to ammonia evaporated from livestock manure, airborne nitrogen compounds contribute to the load in the sea. Air pollution is responsible at the present for about a third of the nitrogen that reaches the Baltic Sea.